Okay, so we're going to start chemical equilibrium. First of all, let's consider a reaction. So let's say you have a reaction A plus B goes to C plus D. Okay, so you have a very basic reaction. You have some reactants, A plus B. Those reactants are going to C plus D. So you have reactants going to products. So when the reaction begins, so let's call this at time t is equal to 0. So at time t is equal to 0, the reaction has just begun. Okay. Will you have any products at that point in time? No products, right? Okay. So let's call it this way. There'll be no C plus D, no products. Okay. So let's say we check as the time progresses. So we go to 1 second, 2 seconds, 3 seconds, 4 seconds. What do you think is going to happen? Are the reactants going to be consumed and products going to be formed? Okay. So what we're monitoring is as the seconds go by. So 1, 2, 3. As the seconds go by, can we say that A and B go down and C and D go up? Now, in the previous chapter, chapter 14, we learned about how fast does A and B go down, or how fast does C and D go up, right? So in this chapter, we're going to say, well, let's monitor what's happening to A and B, and let's monitor what's happening to C and D, but also be aware that at some point in time, you're going to have enough C and D built up out here that there's going to be no longer any more space for C and D to form. So think about it this way. If you ever tried filling a jar with some beans or something? Jar with beans or rice or something like that. So you fill and fill and fill, and right when it gets to the top, you have a little more in the bag. And you're like, okay, I'm gonna have to fill this jar, but I don't have another jar for this little more. So what do? You shake the jar, right? You hit it on the side so that the beans can settle, right? And when they settle enough, then you make a little more room to add more. But that never happened when you started pouring the beans in the jar, right? Because there was plenty of room for the beans too. So at some point in time, so if you think about it, the rate of pouring beans, the rate at which the beans are entering the jar, don't you think that's slowing down over time? Because in the beginning, you have all this room, and then soon when it's getting to the top, now you have to shake the jar, hit it, add it gently so it's not overflowing. So finally, you're going to get to a point where the jar is going to be full. You're not going to be able to take a single bean more. At that point in time, if you add any more beans, do you think they're going to spill over? They will. Same thing happens in reactions. So if you think about those are your beans, they're going into a jar. Well, at time t, the jar is empty, right? Because there's nothing out here, so it can go very easily. So the reaction out here, so that there's essentially two things happening out here. At time t, you only have a forward reaction happening, and that can be depicted by this arrow. Notice carefully, I drew a half arrow, okay? And then what's going to happen is, once the jar fills up, now, if you add any more beans to it, they're going to spill over. So what happens is the C and D are going to initiate a reverse reaction. So that process is going to begin, okay? And now, obviously, we're not dealing with jars of beans in this case. We're dealing with reactions. So it turns out for any reaction, there's a forward process And after some time, once you have sufficient products formed, you don't have to have too many. You just have to have enough to initiate a backward reaction. Okay. So once you have just enough to initiate a backward reaction, then the backward reaction begins. And so you have these two competing processes. Okay. So you have a forward process, and then you have a reverse process. And when the forward rate, so the rate of formation of products, the forward rate equals the reverse rate, then you have a situation of equilibrium, which is also referred to as dynamic equilibrium. Turns out, if you plot the change, this is what it'll look like. So when the reaction starts, and you can actually measure the change using a device like spectrometric analysis or something like that. So you can map what's happening. So if you have a graph out here, and let's say that's time, a reactants start out here, because at time t, you have a maximum reactants, right? And then over time, your reactants will deplete. And then let's say at the end of the reaction, there's your reactants. Change that color. There is where your reactants are. Then what happens? Well, when the reactants are not working in isolation, right? Because as the reactants are depleting, what's building up? Products are building up, right? So at time t, you had 0 products. So here's your products, they build up, and then they're going to stabilize too. But how will you monitor this change? Well, you can use an instrument in the lab to monitor the change, to figure out what's happening. You'll see the increase or decrease of something. But long story short, we're talking about this region. From this point onwards. So see, at this region, if you look at just that part of the line, do you see how those lines have stabilized? They're no longer bending back and forth. So this is where the chemical equilibrium is happening. And just for context out here, these are my reactants, and these are my products. Okay, so